All right, thanks for the introduction, and thanks everyone for coming out today. Our understanding of the origins of planets came from just the 8 planets in our solar system, which was a planet when I was among these planets. We see a remarkable range of properties. We see the small terrestrial worlds, including our own Earth, and then we see the giant planets far out, and they have these very diverse compositions, and really fruitful for understanding planets thanks to the discovery of the planets outside our solar system, the exoplanets. As of March 2025, so I just checked the count, and 49 exoplanets discovered and counting. So as you can see from this histogram, a lot of these planet discoveries have come in just the last 10 or 15 years or so. And when we're looking at thousands instead of just 8, we see even more puzzles in planet formation. So here is a plot showing the distance of the planet from their star and their planet mass relative to Earth. So these white dots and these blue dots show the exoplanets where we have measurements of the semi-major axis and the planet mass. What should jump out at you right away is that these blue dots are in a different part of this plot than the whites. Now, part of this is observational bias, that our observations right now aren't great at finding planets that are like the ones in them, but it does tell us that there are many planets that look nothing like the ones in our own solar system. The planet is Mercury, but as you can see, there are tons and tons of exoplanets that are even closer to their own planets, with orbits that are only long or shorter. These are extremely hot planets, and some of them may even be lava planets because they're so close to their sun. Look at the planets outside now, planet formation is if it's so, and we also have sometimes see these cold giant planets that are out than the planets in our own solar system. So how did they form, and why don't we have one? Well, much like the outcome of baking a chocolate chip cookie depends on the ingredients you put in and the oven that you used, we expect that the properties of a planet should be linked in some fashion to the physical and chemical conditions of planet formation is intrinsically tied to star formation. So out in space, we have these molecular clouds, huge molecular clouds, and sometimes they have so much mass that bits of them will start to collapse under their own gravity. And that's how star formation begins. So during the star formation process, you have gas and dust collapsing in on itself. And then most of that will go toward, some of that dust and gas will instead be spinning around the protostar. And this is due to a process that is called conservation of angular momentum. If you've ever spun around this chair or spun on figure skates and you throw your arms out or you pull your arms in, you'll notice that your spin changes based on how large you've made yourself. So the similar idea applies here. You have a collapsing cloud, and all that angular momentum has to go somewhere, and that is why we get these objects called protoplanetary disks, which are made out of gas, dust, and ice, and they orbit young stars. And when we say young, we mean like a few million years old, which in comparison to our solar system, that is young, because our solar system is about 4.5 billion years old. Million versus billion. So the big picture questions that my research seeks to answer are: where, when, and how do planets form? How do the properties of the protoplanetary disks in which planets are born influence the outcome of planet formation? And what can disks tell us about the nature of planets when they are being born? So I assume that for many of you, this is the first time you've heard the phrase protoplanetary disk. So I just want to quickly walk through what a protoplanetary disk is like. So a protoplanetary disk, like I said, is material orbiting a star. So this diagram is a vertical cross-section, like if you imagine cutting a birthday cake in half, so you could see all the layers. So at the center is the host star, and then it's made up of gas, dust, and ice, as I said before. So the left side is showing you what the dust distribution looks like, and the right side is showing you what gas. So the dust we start with these sub-micron size, these very tiny from the interstellar medium. But in the denser of the disk, these dust grains start to collide with each other to grow bigger and bigger. And that is the first step of planet formation. And as these dust grains grow to crunch down vertically, and they also tend to move inward, so then you have this region of where the grains are larger and can grow. So the starlight is setting the temperature of this disk. It makes the hot layers very hot, but the starlight doesn't quite directly reach down into the lower layers. So what happens is that you have these very hot surface layers where the strong ultraviolet radiation breaks molecules down. We call this the photodisk layer. Then below that is what we call the warm molecular layer. It's better protected from the starlight, so it's not quite as hot as the surface layers, and the ultraviolet radiation doesn't break all the molecules down. And then we have the icy midplane. So this is the same region where we see these dust grains growing. And so the icy midplane is called as such because it's gotten cold enough where these molecules have now become frozen onto the dust grains. So planet formation is a very complicated process with many steps. And we have to somehow get from these tiny submicron sized dust grains into bodies that are many kilometers across. So that's a huge change in scale. And so one of the unfortunate things about planet formation from an observational standpoint that we can't directly see what's happening in the middle. So the reason that protoplanetary disks are important is because this is the last stage of planet formation that we can directly observe until we get to actual planets. So our solar system is pretty old, but it did provide the first clue that planets form in disks. So, I mean, if you look outside, clearly there's not a bunch of gas and dust swirling around our planet. That would be very bad for us. But people noticed a long time ago, centuries ago, that planets in our solar system all orbit together in like a flat imaginary plane. So they said, well, that seems to imply, how did they get in that plane? That seems to suggest they all had to form in some kind of disk. Although back then they called them nebulas. It took a while for the first observational evidence that other young stars had disks to emerge. So this first evidence came in the form of what we call infrared spectra. So measuring the amount of light that comes as a function of wavelength. So our sun's spectrum has this characteristic shape. It goes at short wavelengths, it peaks up, and then it has a peak at visible wavelengths, sunlight, that's what we see, and then it drops again. But then when they looked at young stars, they saw that their shape didn't quite resemble that of the sun. Like on the short wavelength side, it matched up pretty well. That was from the starlight. But it's this extra infrared that the sun didn't have. So the explanation that astronomers came up with was, well, there's got to be some objects there that are creating this extra emission at these longer wavelengths. What is happening is that there is dust around the stars. That dust is absorbing the radiation from the star and then radiating it back out at longer wavelengths. And so this was exciting because if there are disks around other planets, around other stars, then this implies that there can be other planetary systems around other stars. So this was in 1966. And you may look at this and not be totally convinced, which is fair because there were a bunch of astronomers who were not totally convinced. They thought about, well, there could always be other explanations for why you have this dust, why you have this infrared emission. So, you know, as answer is worth 1,000 words, and it's a lot easier to convince astronomers if you have a good picture. So, the Space Telescope took pictures of the protoplanetary disk in the 1990s. So people were arguing about this for quite a while. And here you can unmistakably see they're circular. The reason that these look like ovals is because you're looking at them at an angle. So one thing you may notice is that all of these disks look black. It's not because they're actually black. It has to do with the property of the dust grains in the disk. So dust is going to block more emission of the same field at different wavelengths. So at the short wavelengths, you see this big black patch. It's not that there's a hole in the sky. It's because this dust is stopping the starlight behind it from coming through. As you go to more and more transparent, and you start to see more starlight poking through. So the Hubble Space Telescope observes from ultraviolet to near infrared wavelengths. Silhouette, this implies that we need to go to longer wavelengths. So radio telescopes are powerful tools, therefore, for studying planet formation for a couple of reasons. First of all, because of grain growth, a lot of the disk solid mass is in centimeter sized dust grains in the midplane. This is the planet forming disk. And conveniently, dust grains of this size produce very bright emission at millimeter wavelengths. But it took a long time for telescopes that could really do a good job of imaging disks at millimeter wavelengths. There are a lot of challenges. First of all, by astronomical standards, protoplanetary disks are not that big. So the typical size of a protoplanetary disk might be somewhere on the order of a few tens to a few hundreds of astronomical units. So just for reference, an astronomical unit, or 1 AU, is the distance between the Earth and the Sun. Not only are they not intrinsically that big, but they're not that close to us. You know, our sun is old, it's not in a star-forming region there, and so by definition, these protoplanetary disks have to be in young star-forming regions. And so these regions, the ones that we think of are several hundred light years away. And so if you wanted a telescope that could resolve a protoplanetary disk, the scale is like standing at one end of the island of Manhattan and then trying to see a piece of fruit at the other end. So there's an added difficulty if you want to observe at millimeter wavelengths. So the sharpness of the image you can get, the amount of detail you can see, or the angular resolution from a telescope, theta, is approximately the ratio of the wavelength of the signal that you're observing at over the diameter of the telescope. And like I said, millimeter wavelengths are long wavelengths. So that means in order to get good resolution, you also need a big telescope. So if you can start to get a semi-interesting picture of a protoplanetary disk at millimeter wavelengths, you would need a telescope dish diameter that's larger than 100 meters. And that's not super practical. There are telescopes that exist that are larger than that, but they're not fully steerable. They're staring at one part, and so you don't want to be just staring at the same disk for your entire career. And so for comparison, the Hubble Space Telescope observes at shorter visible wavelengths has a diameter of only 2.4 meters. So that's a lot more manageable, but it's also not ideal for making the kinds of observations to study the interiors of disks. Luckily, some clever people figured out a solution to wavelengths about 100 years ago, and that was through something called interferometry. So the idea behind interferometry is instead of having to build one humongous telescope, what you can do instead is you can build a bunch of little telescopes and put them far apart from each other. So the astronomical signal will reach those telescopes at slightly different times, and by using a computer, you can reconstruct what the original signal had to look like in order to create the delays to those different telescopes. And so now your angular resolution, instead of being inversely proportional to the diameter of the telescope, it's inversely proportional to the separation between the telescope, the baseline. And so it's a lot easier to put two telescopes really far apart than it is to build a humongous telescope. And this technique may sound familiar to you through a completely different context. So I hope that some of you remember seeing on the front page of the New York Times the first picture of a black hole, and that also made radio interferometry. Now, funnily enough, this actually looks a lot like a protoplanetary disk. So here are the state-of-the-art disk observations about 14 years ago. And trust me when I say that these images are actually thrilling. They're pretty blobby. You can say how big the disk is. You can say maybe how much material there is. And they're different sizes, but you think, okay, well, these disks kind of look the same, right? And just to kind of explain some of these symbols, this little circle you'll see in a lot of these images, that tells you the resolution of the image. So if the circle is very small to the image, that means we're getting a lot of detail. Another note I want to make is that these color maps are arbitrary because these are radio waves, don't correspond to the true colors of the disk, but it's just let you know how much light we're detecting. It's very bright at the center, so we're detecting light, and then further out, we're detecting less light. Along a bit more than a decade ago, it's called the Atacama Large Millimeter Array, or ALMA for short, because that's a mountain. And so the Atacama, well, I don't know why I started saying the whole name again. ALMA is a huge telescopes in the Atacama Desert of Chile. And they put all these telescopes really close to doing actual science operations. And the reason it's located in Chile is because there's a high and dry site far from people that has great weather for observing. So with ALMA, we were able to perform the first, we call this survey D-sharp for short. We looked at 20 bright disks, and unlike the blobs that we were seeing before, we can now see a remarkable amount of detail in these disks. And what we see is that no two. So we see lots of different kinds of features. We see these gaps and rings, and then sometimes we even see spiral. So there's nothing that you see in galaxies. And so the resolution of these images is approximately 5 AU. So for reference, that's approximately the distance between, from just being visually interesting. The reason that these structures were really exciting is because theorists predicted that you might be able to get these kinds of structures through the gravitational interactions between a protoplanet and its disk. This hydrodynamical simulation shows a sped up version I think might be happening, but to be clear, we think this planet formation process is taking place over the course of 1 million years or so. As a function of distance from the star in these disks, you can clearly see the gaps and the rings at different locations, and they have different widths and depths. Now, if you buy the planet formation, the planet-disk interaction explanation for where these gaps and rings come from, then you can compare the simulations of planet-disk interactions to gaps that we observe in order to try to figure out what kinds of protoplanets would you need in order to create these disk structures. So if you look at the measurements from D-sharp, the comparisons of the simulations suggest that the planets have these properties, the semi-major axis here, the distance from the star, and the planet mass over here. So the solar system planets are shown in the big circles, and then the exoplanets, the known exoplanets, are shown as these little dots, plotted, color-coded by their detection method. So I should, again, jump out you at this plot, is that the measurements for the inferred properties of the planets in the disks that we observed with ALMA are in a different part of space than the exoplanets. So this raises the question of whether this is because our existing exoplanet detection methods aren't good at finding these kinds of planets, or if this is telling us something about the evolutionary history of these planets, that either they're going to continue growing and then join these massive directly imaged planets up here, or if these planets move inward to join this population of planets over here. This isn't a question that we can readily answer yet, but next year the Roman Space Telescope is going to launch, and it's going to use this technique called microlensing that should be very good at finding planets out here if they exist. That's not to say that we can't see protoplanets at all. Right now, read in optical observations with telescopes such as the Very Large Telescope in Europe, which is a very creative name, and the James Webb Space Telescope, they're being used to look for emission directly from the protoplanets themselves. When protoplanets are born, they are very, very hot, so that allows us to see the emission from them directly, which is something different from the planets in our own solar system. They're not hot anymore. And so in a few cases, we can see planets inside disk gaps, which does give us some confidence that there's an association between planets gaps. But right now, this technique is, for the most part, limited to planets that are sort of maybe a couple Jupiter masses or more. And that's pretty massive. We don't think that those planets are super common. So for when we go into planets that we think might be less massive, disk gaps are still great for trying to understand the formation of planets that might be more on the order of Saturn or Neptune. In addition to gaps and rings, ALMA has found several examples of what we call these grand design spiral arms throughout the entire system. And there are several ideas for how these excite these spiral arms. But another intriguing possibility is something called instability. So simulations have shown that when disks are very cold and massive, they can become unstable. Another thing that can happen, though, is that the instability disk causes fragment, and those fragments could eventually form planets. So one question in planet formation right now is gravitational instability a pathway to make planets? So to be determined. One limitation of what I've shown you so far is that, as you might imagine, it's easiest to look at the disks that are in the star-forming regions closest to us. But that doesn't necessarily mean that those disks are typical disks. So in fact, a lot of the star-forming regions near us have pretty low external UV radiation. But it's believed that most stars, including our sun, are likely to be born near these massive stars that produce a huge amount of radiation. And if you've ever gotten a sunburn by staying out too long on a sunny day, you know that ultraviolet radiation. Theories suggest that high UV radiation can be damaging to planet formation. What can happen if you're too close to a massive star is that the UV radiation will actually cause a process called photoevaporation, where the disk actually starts to lose material from its outer regions. Then that's not great for planet formation in principle, because it'd be like if you tried to build a house with a bunch of bricks and someone was carting away those bricks while you were trying to make the house. So, and there is evidence of this external photoevaporation that from lower resolution ALMA observations. So one region that astronomers radiated by a multiple star system, also called a Sigma Orionis, so that includes an O star, the most massive and hottest kind of star. And if you look at how far away the disks are from that massive star, and then you look at their mass, you see that the massive disks are far away from that massive star, and then nearby that massive star, you only have very low mass disks. So this has been interpreted as evidence of external photoevaporation causing disks to lose mass. So given this evidence that this ultraviolet radiation can be damaging to planet formation in this sense, we were curious whether we should still see these nice rings that we were seeing in the disks in nearby star-forming regions. So we used ALMA to obtain the high-resolution images of disks in this star-forming region. This is more difficult than the observations from before, because this star-forming region is 2.5 times farther away. So you're really pushing on current limits. But reassuringly, even though the external FUV fields and the disks that we were observing before with D-sharp, we still see these nice gaps and rings in many of these systems. And this suggests that whatever process is forming these gaps and rings, whether it be giant planet formation or some of planet formation. That being said, there are disks that are in even more extreme environments. So one of the open questions is, how extreme can we go before we stop seeing disks that look like this? So millimeter interferometry is a 2-for-1 deal. Not only can you see the dust grains that will eventually grow into rocky planets and the cores of giant planets, you can also see the gas. So you can see molecular lines from, you can see, so they have fingerprints at unique sets of wavelengths or frequencies. And the high energy levels happen at short wavelengths, but disks are very, very cold. So generally less than 100 Kelvin. So that means that we want to look at a kind of transition called a rotational transition, where the molecule is just kind of moving or rotating in a quantum mechanical sense. And so conveniently, those transitions happen at millimeter lab, what frequencies those transitions should happen at. And as astronomers, we can then see if those transitions are in our data. So I think it surprises many people to learn that the inventory of molecules that have been detected in space is quite rich. So even disks are really nothing compared to the other kinds of regions that have been studied. But we have a pretty rich chemistry in disks that's been observed already, with molecules, some really small molecules, just 2 atoms, and some that are rather larger. And even this table is already out of date because there have been a few more complex species detected. So some of these species are those that are familiar to us on Earth, and some of them are a lot more exotic. They would never survive stably on Earth, but in interstellar space with the different densities, temperatures, and pressures, they do manage to stay stable. So we can divide these molecules into a few different groups. The organic molecules, which are particularly interesting to those who are interested in the origins of life. Things like formaldehyde, methanol, and then things containing carbon and nitrogen. Other small neutral molecules, the most interesting of which perhaps is water, since we need water to survive. And then molecular ions, those are definitely not the things that you just find floating around on Earth because they would never be stable here, but very important in disks. And then we have what we call the rare isotopologues of the common disk molecules. So these, if the number of neutrons is different, then that's what, then you have different isotopes. And so the chemical properties are slightly different. And the reason these are interesting, I'm not going to get too deep into this, but we can use isotopic ratios to track history because the isotopic ratio is responsive to the physical and chemical processes happening in disks. So where molecules are abundant or rare in protoplanetary disks is shaped by a variety of processes. So things that are important include the amount of radiation it's getting, the temperature at a given location, external UV radiation, perhaps from a massive star nearby, the growth of the dynes and their travel through the disk, the amount of things that are being mixed throughout the disk. And so this leads to a very complex distribution of molecules. So here are observations from ALMA showing different images of the same protoplanetary disk, but in different molecules. And so the details of the molecules in here, but the main takeaway is that these images look different from each other. In disks, you can see there's only a lot of emission near the star and then nothing far out. In some disks, you can see there's not a lot of emission near, but there's a lot of emission far, and more extreme even in this one. And so that's telling us that the chemical properties of the planet that you make depend on where you form in the disk. And so this is a particularly exciting time to study chemistry, thanks to the James Webb Space Telescope. Because what the James Webb Space Telescope is really good at doing that other observations of the atmospheres of the outside of our solar system. And we can detect molecules, some of them, like the ones in our own solar system, water, and then, but also some more exotic molecules. And so the question is, can we link the exoplanet compositions that are observed by the James Webb Telescope to their location in the disk where they formed? And so this is something that's still very much a new thing. The telescope has been operating for years, but this will be one of the big goals of planet formation and exoplanet studies probably over the next decade or so. So the disk observations I've shown you so far, you think, oh, everything looks really nice and neat. I could a bunch of rings and I've got a disk. Well, that's because I waited to show you the more complicated stuff. So if we look at carbon monoxide observations, you don't always get these very nice symmetric rings. Sometimes you get these crazy looking, almost galaxy-like structures with these huge arms, tidal tails, these little streams of gas around them. And the reason we get this level of complexity, we think, is because of interactions between disks and their environments. And so what kinds of interactions can occur? But that's not the picture that you should walk away with. It's to remind you that these disks are forming in star-forming regions. So there's stars around them, and there's lots of gas and dust around them. So there are a couple of things that might be happening in these disks. So star-forming material around them. And then another is that if a star comes really close by, that's what we call a stellar encounter, it can rip material out of the disk. So while we're still observationally and theoretically exploring the consequences of what these external disturbances can do, there seem to be hints of the following effects on disks and then subsequently on the planets that form within them. The most simple one is that they seem to affect the disk mass and the size. And those are pretty fundamental quantities for determining how these planetary systems can develop, because if you don't have material at a certain radius, you're never going to be able to form a planet. If you have more mass, then in principle, you have more material to make planets. Another interesting thing that these processes have been predicted to do is that they can create inner and outer disks that are different orientations. Now, remember, in our solar system, our planets are orbiting in almost a flat imaginary plane. But if you have the inner and outer disks separated from each other like that, then you can have some wild orbits where one planet is orbiting and then another planet is orbiting like this. And in fact, there are exoplanet systems that do have that behavior. So the question is, does this why those planetary systems look like that? And another interesting pathway is that there seems to be some evidence that you're dumping material onto the disk. It's changing the chemical composition. And so that makes the goal of linking exoplanet compositions to their formation location in the disk more challenging than we had previously thought, because this kind of process was not taken into account. So it's an exciting era to study planet formation, and we're still only really scratching the surface learning about disk structure and chemistry. I've been showing you results of deep observations of a few dozen disks, but there are hundreds of disks that we know about, but we just haven't seen. So pretty much every disk we've seen so far offers its own unique take on planet formation. So we haven't explored all the possibilities yet. And then there's a lot that we can do over the next couple of decades to learn more about formation. So I already showed you some of what James Webb is doing to try to link disk to even better, because in the next few years, we upgraded to allow us to do those more extensive studies of the population of this. And looking even further ahead, the next generation very large array to be constructed in the southwest of the United States is under development. It's being focused on the outer giant planet-forming zones of disks. We can look even closer and closer at the inner solar systems. So thanks for your attention, and I'm happy to take questions.